Today I'll tell you about support vector machines or SVMs. So SVM is quite similar to logistic regression. The intuition is roughly the same with slight twists and tweaks. So let me just give you a rundown of how logistic regression works and its equation just quickly. So logistic regression is basically, our motto is to separate two class labels. It's a classification algorithm actually, to separate two classes via hyperplane or a line in 2D, and of course we are assuming that our classes are linearly separable. So our motto is to find the best plane that best separates both the classes. So the final equation is, we need to find the plane. We are calling the plane as W star, and we need to maximize the distance between the two classes. Hence we are maximizing the distance between the two classes, that is yi w transpose xi. And for logistic regression, if it's correctly classified, then your yy and w transpose xi will be 1, and if it's incorrectly classified, it will be -1 if correctly classified. If incorrect. Alright, so there is a quick rundown of logistic regression. I don't want to extend it much further. So for SVM, the intuition is very much similar. Again, here we are trying to find a hyperplane that best separates both the classes. But there is a twist. The twist is, what if, just for instance, what if our point is very close to the hyperplane? What if another point is very close to the hyperplane? So in order to avoid this, what we are doing is, we are trying to create another two planes that will better differentiate our margin between the two classes. So what do I mean to say is, suppose this is our positive class and this is our negative class. So we will draw another plane with the points, or the point that is closest to our hyperplane. So these 2 points are closest to our hyperplane, hence we are drawing another plane that is pi plus, indicating the positive class label. And similarly we are drawing another hyperplane passing through the points that is closest to the hyperplane. Again, here are 3 points that are closest to our hyperplane, and we are drawing another line through here and calling it pi minus. So if this equation of our main hyperplane is w transpose xi plus b stands for bias. So this is our classic equation of our primary hyperplane. So for the plus, we are increasing, let's just say this distance is d. Let's, for example, let's just say this distance is d, this one is d. This one is actually negative d because we're going to the negative side of it, and this is positive d. So our equation becomes, over here, it's for the positive side is w transpose xi. Let me just write it down. For the positive side, it becomes w transpose xi plus b equal to +1, and for the negative side, it becomes w transpose xi plus b equal to -1. Actually we are not sure about the distance between, it can be anything, it can be 2, 3, 4, 5. we are just taking -1 and +1 for simplicity. And yes, this is the equation of pi plus and pi minus. So yes, again we are trying to maximize the plane that better separates the class labels. And so our SVM equation is, we are trying to find the best W and the best bias. How? By maximizing our W and B. Our W is basically the distance between our margin, the distance between the two planes, pi plus and pi minus. So we are trying to maximize this particular distance. This again, we are taking 1 for simplicity, plus 1 and minus 1 just for simplicity, and it can be anything. It can be 2 or 3 or 4, whatever you want. And yep, we are trying to maximize the margin distance between the class labels. So why is it called support vectors? So because our pi plus and pi minus is passing through the first points that are closest to the main hyperplane, that is pi. So these points which are closest and the two other planes, that is pi minus and pi plus, is passing through, these points are known as support vectors, hence the name support vector machines, SVM. And for pi for all the points that are passing through pi plus and pi minus, our equation, our primary equation, that is yi w transpose xi plus b, is actually 1. I'll tell you why. Let's just take this point. So for this, our class level is -1. Sorry, my bad. -1. And if our model predicts it correctly, so it will be -1 as well. So w transpose xi plus b is equal to -1 as well. Oh boy, -1, which becomes +1. -1 multiplied by -1 is +1, right? So let's take this this point. I'll show you it over here. So this is positive, so the main class level is positive, multiplied by the predicted. If it is correctly predicted, it will say it's +1, hence it's +1. 1 into 1 +1. Yeah, anything else? Yeah, so this is a quick rundown of support vector machines, and always remember that our main motto is to maximize the distance between the pi minus and pi plus. Again, pi minus and pi plus. I'll give you just a quick example so as to why we need to do this. For instance, this is your plot, and this is your friend's plot. This is your friend's plot, this is your plot, and suppose your friend makes his house till here and extends, and there is a high chance that he can extend his balcony on probably the second floor to your side as well, so that this is a sign of encroachment, right? So in order to avoid this, we are we are sort of declaring that you won't make any structure beyond this, and I won't make any structure beyond this. We'll keep a fine gap between both of us, just like what happens in the international borders. We're trying to make a fine gap between both the borders, and that is called the no man's land. So this particular thing is the no man's land. The distance between pi plus and pi minus is the no man's land, to better separate and to give us the better demarcate, or to better indicate that here is our positive class and here is our negative class. I'll go much more deep into SVM in the next videos. Thank you so much for watching.